My name is Sergio Ammirata. For those who don't know me, my company name is SipRadius, and I'm also a director on the Rist forum. We're going to talk about how Rist enhances IPMX for production and monitoring streams, which is nicely placed right after the IPMX talk. So first, as we saw, IPMX stands for Internet Product Media Experience, and VSF has developed all the technical recommendations, and it's near the end of the first round, I would say, because one thing that still needs to happen is how do we add the other side of the coin, the compressed data, the Rist inside IPMX. So this will be primary focus on how we can improve IPMX through sharing and passing timing and sources over public internet with compressed formats. And our orange is going to be 2110. We're going to discuss how to reproduce the timing across the internet. And the Spectral proposes, like you saw, doing it with PTP clocks or NTP or even without a clock. So IPMX is going to be a central part of this discussion, but we'll place it within a context of a large project, a large deployment, more like a use case that we have, where the concepts come into play. We've been working with one of the big 3 US broadcast networks for a while now, and that project uses Rist to share many feeds between New York and London origin points. We then distribute those streams to all types of locations all over the US and the UK. Production personnel, engineers working from their home, executives, various locations, all have to monitor and work with these feeds on a daily basis. So this talk will trace those feeds from the 2110 origin points all the way to the end users. All right, so first, let's look at the first step in the process. We go from a 2110 encoder in London or New York to a Rist sender. Okay? As we mentioned before, there are encoders and Rist senders at both locations in London and New York, and those streams have to be distributed to multiple locations where there are additional Rist receivers. Users can be anywhere, and the headquarters offices, other offices, or even working from home as it happened during the last 2 years. So the scope of this project is quite big, as far as number of streams and number of users. And at the core of all this, we use an open source library called LibRist. I should mention as well that I'm the principal architect and maintainer of the library. The library is a free and open source project, and we use it throughout our business, our products, etc. And the only proprietary piece that we add on top of this library is just a fancy web interface. Everything under the hood is the exact same library that anybody can use, unaltered LibRist. So, as we look at the first step, the encoder, we'll start looking at how IPMX fits into all this. So let's talk about the encoders. The encoders are our own high-density 2110 to H64 hardware devices. They can do 20 encodes on each machine, and every machine includes a PTP synchronization software. So we have the clock synchronized to within a few nanoseconds of the local clock source at the different locations. In the VSF technical recommendations for IPMX, NTP can be substituted for PTP, and we do that in the other steps of the chain. In addition, though the demos and everybody has focused on JPEG XS as the codec for compression, it's not, the spec doesn't restrict you to that. In our case, we had to use H.264 to achieve viable compression for transport to the end users in the different places. The main takeaway, however, is that it's about synchronizing playback across long distances, across devices, and reproducing the timing and synchronization of audio, video, metadata, etc., in all parts of the program as perfectly as possible, even with the user at home of our web browser. Okay, so what were our design precepts? Bearing in mind that standards are still evolving, and we've been at this project in one way or another for the last 1 or 2 years, we had to make some assumptions of where the spec would go, right? First, we assumed, as we saw, that nobody would want to send 2110 over Rist anywhere, even with LC4 compression, which is, by the way, part of the advanced profile specification in Rist. But in any case, just about everyone is going to go and encode to a compressed codec. You then encapsulate that compressed format in either 2110 RAW or MPEG-TS, and then push that over Rist. One of the a little bit of a pitch here, one of the talks I submitted for NAB was our 2110 over JPEG XS over Rist for NAB IP showcase. But anyway, the point is there has to be a compressed format. We can do then encapsulation over 2110 or MPEG-TS, and then use that inside a Rist tunnel to transfer over logged instances, and Rist has all the capability to transmit timing information and other things in the protocol itself. JPEG XS is going to give you the lowest latency, highest quality at the expense of 300 megabits per second. But in our case, we needed our streams to be anywhere from 3 to 6 megabits per second. So H.264 was used. Bandwidth is one of the reasons, and we'll see all the reasons why we use this codec in our transmissions. In any case, our goal is to allow the encoder of everything. We even though we go H.264, we still want to send, and we did MPEG-TS instead of RAW 2110. We take and send all the ancillary data coming from the source. Closed caption, whatever, timing information, all the video and audio tracks, etc. And of course, down the stream, we added options to remove part of the pieces so that we don't send, stuff that the end viewer doesn't need. The idea or the goal was to have an IPMX experience from beginning to end. The data has to be there end to end for the IPMX experience to be adequate. So what's our approach? As a company, we want to be the live streaming king. And the key to this is flexible workflows, right? What did we do to achieve this? We put the Rist receivers inside the media servers themselves. Like I explained, we use the encoders to create all the video audio codecs needed for playback anywhere ahead of time. So we prepare the signals from the beginning to be what we need them to be for all the users that are involved in the process. We maintain all the ancillary data, but strip the nulls for efficiency. There were some requirements that closed caption had to be displayed in some of the end user devices. We included a full DRM workflow that allows web browser playback, and we also had STB access, set-top box access to the original unaltered MPEG-TS that comes straight from the encoder to the end users. And part of the premises was the user can be anywhere. Doesn't have to be geographically close to the media servers, to the encoders, or anything like that. So let's double back to the encoders and provide a little bit more detail of what the encoders do. Our encoders. One of the things we feel keenly about, because our particular solution is an OS that can be installed anywhere and that can perform all the tasks. So we feel keenly about the fact that you have to decide what's most suitable for a VM or cloud, versus what's suitable for big hardware or small hardware, even for small hardware. Obviously, for the 2110 case, we needed powerful hardware for this. And at the end of one of the last slides, I'll show you the counterpart, the smallest hardware that we use for some simpler encoding. In this case, our machines are extremely large, powerful machines that can do 2110 over just COTS, off-the-shelf hardware. One important thing that everybody knows is that these 2110 streams, they can be big and demanding. In our case, the original streams were either 1.5 gigabits per second or 3 gigabits per second, 1080p and 1080i, respectively. Our servers, our encoder servers, can use either Mellanox or Intel cards. We're not tied to a particular SDK. However, we do use the custom drivers. Our system is based on Linux, the custom drivers that bypass the network stack completely, so that the OS does not become a bottleneck. Our encoders, each of them can handle 20 streams, 20 basically 2110 streams coming in, and we can produce two H.264 video tracks for each at different resolutions and bit rates, and we can produce 32 audio tracks on each stream, and 32 because we actually create 16 AAC audio tracks and 16 AAC Opus tracks from the origin uncompressed audio tracks. And then we send all those down the chain for the different, to be able to be distributed to the different viewers. We create multiple NVIDIA audio profiles to accommodate all the possible playback devices, and we want to basically minimize or eliminate the need for transcoding down the chain, which would introduce significant latency. Latency is a big deal here. Our ultimate goal is, we want from the encoder all the way to the user, wherever it is, whatever device, we want at around 1 second glass to glass was our goal for these projects, and we achieved it using all the steps. Finally, we configure all of our encoders with a Rist sender. It's part of the encoder on listening mode. This is the core of what we're hoping to coin as Rist on-demand concept. And we'll explain that later in another slide. The Rist sender is the encoder sitting there with a Rist sender in listening mode, waiting for somebody to request a stream to be dispatched somewhere else. Okay, next, pushing to the media server. The first step was the encoder. Next step, we're going to push the data to the media servers. How do we do this? We put the Rist senders, like we already talked about, inside the encoders in listening mode. And then that basically outputs to the local networks. It's available in the local networks as a public IP or IP that we can reach to in the New York and London bureaus. Then we have the Rist receivers inside the media servers in VMs anywhere where they need them. So the media servers, which are more like a type of smart Rist relay or media relay, they can be spun up wherever they're needed, where there's a lot of users. In our case, there were 2 farms initially, one in New York, one in London, then we opened another one. The customers spawned a few more in Washington, D.C., and now LA. But the point of this one is that, that's the intermediate step, the relay point that's going to serve the stream to the users. So the users never talk directly to the encoders. They have to go through this intermediate point, the media server. There's a load balancer that we also have as part of our solution, that based on the source IP, will connect the customer or the set-top box or the web browser to the appropriate media server farm. And then the media server itself will initiate a Rist receiver connection to the encoder when needed. So let's look now at the actual delivery mechanisms to the end user. That is, once Rist has hit the media server, we go from the encoder to the media server whenever it's needed, and now what happens next in the chain. So as we mentioned before, we're serving WebRTC to the viewers. Actually, I mentioned web browser, but it's really a web browser with a WebRTC protocol. We created a DRM compliant solution for the management of these streams. We actually had to go through a 6-month security audit to call this DRM compliant. Because as you know, WebRTC itself doesn't have an official DRM on it. So we had to put a DRM layer on top of it so that the major network would accept it as a solution for distributing these very secure streams to users even in their homes. The goal was that the user can just log in with their SSO official username and password and select the stream and play it from a web browser. And the beauty of the system, by using the codecs that we did and the WebRTC for the web browser, is that you only need a web browser, and it works on every desktop and mobile device without any installation of any kind, and you get a glass-to-glass latency of about 1 second. From London to a viewer in LA, or from New York to a viewer in the UK, whatever it happens to be. Now, this is a picture of what the corporate viewer would see on the web browser. On the bottom, you see a pretty Netflix-style carousel menu. That's the typical interface that shows up on the mobile devices. Makes it a little bit easier to scroll and select your live stream. But since the system has a couple of hundred program choices, live streams that they can select, the hierarchical menu at the top right is what is used typically and by default by desktop web browsers. In the desktop web browsers, you select location on the top, you select categories, and then within the categories, you select the channel you want to play. In addition to that, a much appreciated feature that came after the fact and became one of the most important aspect of the system is that we added the ability for the user to create their own multi-viewer. The user can go in there, say, I want a 2x3, 2x4 multi-viewer. They drag and drop the channels into the screen, and suddenly, boom, they have a custom multi-viewer just for them. And our multi-viewer grabs the stream of lower bit rate that we created. That's why we ended up creating 2 video bit rates, so that we don't overload their bandwidth or their playback capabilities. So they ended up using this all over the place, creating their custom multi-viewers, 2x2, 3x3, and using them on their own web browsers. So let's talk about scalability now. How do we achieve the scalability? Why, we didn't have any bottlenecks in the system because from the ground up, it was designed for scalability, and because of the way we have our solution architected, we control every aspect of the project. We actually are the encoder, the Rist gateway, we are the media server, we are the player, and even the set-top box, you will see. We do it all end to end. Our solution gave us the ability to really optimize the workflow for what was needed to create and make this really scalable. You can see in this diagram what we've described so far. There could be hundreds of streams at a time going out from the multiple Rist sender to the Rist receivers. 80 to 100 streams going back and forth between London and New York is not uncommon. And then there can be many viewers watching those streams on either side. As a matter of fact, it's typically thousands of viewers on each side, and these are corporate viewers. This is a large organization. Furthermore, each viewer, each client connected to a web browser can be pulling multiple streams at the same time with their multi-viewer, because our multi-viewer actually has independent streams, one for each tile on it. So the client requests the programs for the variables load balancers. Behind the load balancers, we have media server farms, what we call media server farms. And because all of our media server farms, anything that doesn't require a specialized network adapter like a 2110 input can run in a VM, it's easy to spin up our solution and nodes and just scale up whenever they need. They started with a smaller number of media servers. Now they're up to 8 in New York and 2 in London. And it's easy to just scale up the solution as fast, or as big or as small as you need it to be. Okay, so if you were to stop at the VFSF booth, we were doing a demo on our mini PC, right? Except for 2110 encoding, much of what I've described here can be accomplished at a very reasonable price with smaller hardware. You don't need to have this beast of a machine where you were using for 2110. And most parts, such as a Rist in particular, is not CPU intensive. So even the VMs you need to speed up to spin up are small, and they're not to be, the media server dispatching the streams, because we've eliminated the transcoding from any of the middle tiers. Our media servers are very lightweight. All they're doing is just distributing data to the different viewers. The point is, this solution can also be deployed at a very small scale when needed with SDI or IP sources. Not because I'm showing here this mega deployment, doesn't mean that you cannot have a system with 5 encoders, IP, and just 10 users viewing this in a secure way. So this is just a picture of the fanless i7 tiny little device. We use similar units, form factor, downstairs in the demo. One of them was the network one, and the other one was one that had SDI input and SDI output. So let's finish up the stream's journey now and discuss the other method, the alternate method of how the streams arrive to the end user, okay? So we created basically a set-top box. With a view that the least hardware is sometimes the most cost-effective, we created our own set-top box. This is mainly for the personnel at headquarters and other key locations that needed to have a fixed monitoring system, executives that don't want to have a browser open on their other monitor because they need to have Outlook there or whatever. They had a dedicated set-top box with a dedicated monitor connected to it and a remote control. We basically ported our proprietary Linux OS that I've been talking about, that we run all of our encoders, media servers on. We ported that to the Raspberry Pi as well. And we wrote a custom interface, user interface for it, which brings us to security and authorization. How do we do all this security? We should note that Rist already has AES encryption and SRP EAP256 authorization on it. So the stream transmission itself was already highly secure, but that was not enough in this case, right? We had to add individual and group access control lists based on the login credentials to control who can watch which streams and make sure that accidentally somebody that's not supposed to be watching one particular show, the production one show, watches a different one. Obviously, the point to make here is that the more security choices you have, the better. And in this case, we had to add all this before the solution could be accepted to transmit all these ultra-secure streams. The user interface in our set-top box was designed to be as simple as possible. There's going to be non-technical people operating these devices. So all the menus options are only one layer deep. There's not a context menu or this strange thing. We actually didn't even put a keyboard on our remote control that like most users do, because we were able to achieve everything in a simple enough way. At the same time, we added some advanced search and filtering capabilities at the set-top box, so the user can select between a smaller number of their favorite channels, since the list is typically hundreds of channels at a time. So Rist on demand. We wanted to add one more note, and that is, it isn't really apparent. I mean, I mentioned it a couple of times, but in the slides, I don't talk about it much. This is something anyone can do. It's absolutely standard Rist. We have not modified Rist in any way or bent the specs. We just did the fact that we control the entire OS, allowed us to do some fancy scripting and binaries and services, and we created what we call Rist on demand. So because there are so many feeds and programs, it's not realistic to just send everything from London to the UK, so to New York and to New York to London, because it would take an enormous amount of bandwidth for channels that are, or streams that are hardly ever used. It's only the ones that are being watched that we're interested on. So whenever somebody requests a stream, that's when the connection, the Rist connection to the encoder happens from the media server. when there are no more viewers, that this Rist connection stops. So that's what we call, or we coin as Rist on demand, the connection between our media servers, which are the gateways to the content and which have the DRM built in, and the encoders, which are now protected devices, behind the scenes in wherever they are. In this case, I showed UK and New York, but this could really be encoders anywhere in the planet. And because we use Rist to communicate from the media servers to the encoder, it's irrelevant if you're going across the internet, across a LAN, if there's packet loss, the data is recovered automatically. Now, what happens when multiple viewers connect to a media server? Perhaps there's a WebRTC viewer and there's a set-top box viewer. As long as somebody already started the stream, the next person that connects is going to reuse that Rist connection that brought the stream over, and then both of them are going to receive the same stream, saving in bandwidth as well. It's not like each user is not connecting straight to the encoder. Users connected to the relay media server, the smart media publisher, which then opens the Rist connection on the fly. When they all stop viewing the channel, they change the channel to something else. 15 seconds later, the Rist tunnel is shut down, saving bandwidth and resources. So in summary, we have shown how we can build a scalable IPMX workflow, even though I bent the term IPMX quite a bit in this talk. We have shown how Rist can be leveraged for on-demand flows across lossy networks and give you, a lot of savings. And finally, I think that we can see how this type of real-world deployments are key to fine-tuning the specs for both future Rist or IPMX, technical recommendations. Thank you.
Thank you. So when you were talking a lot about product that you have, I want to make a point that you were talking about people could use Rist and other technologies in this way, right?
Correct.
You're not up here specifically promoting your product, right?
No.
Okay, thank you for that clarification. Stop talking. Stop talking. We're good. I just wanted to make that point that you and I are on the same page.
Yes.
Okay. Does anybody have any questions? All right. Thank you so much.